So we're going to look at graphs of parabolas. Parabolas are obtained when we plot the quadratic equation. And in this, there's the quadratic equation with which we're familiar. So we're going to look at how the shape of the graph changes with the coefficient of x squared, which is a, coefficient of the x term, which is b, and we're going to look at the, how c changes the variation. So here in box 2, here I put a text entry in box 1. Here I put my three equations in, and I'm going to look at a being greater than 0 and how changing the value of a changes the shape of the graph. You see the value of a here is 1, here it's 2, and here it's 4. You can see, because you've got this line here, that the graph will be part of these are color-coded to match what's over here. So the inner one right here is a equal to 1, and the outer one is a equal to 4. So the middle one is a equal to 2. That's this one here, the sort of blue-colored one. Right in the middle comes down here and then comes up here. So what I said here, assuming a is greater than 0, as the coefficient a increases, the smile becomes wider. So now let's take a look at how b changes in the equation y equals ax squared plus bx plus c. Now, in this case, I'm just going to assume that the coefficient of a stays the same. It's always 1. And we're going to change b, which is the coefficient of x, to 0, 1, 2, 3. And we're going to see two changes. First of all, we're going to look at the axis of symmetry value, x, or minus b over 2a, which shifts to the left. See, here's the axis of symmetry for b equal to 0. It's right along this line. If you go to this one here, which is represented by this graph, and the b is 1 here, you can see the axis of symmetry is approximately there. And here, in b equal to 2, it is approximately there. And here where b equals 3, it's over there. So what happens is, as you increase the value of b, the axis of symmetry shifts to the left. It moves from here to over here. So it moves to the left. So you could also say that it decreases as b increases. Now you'll notice one other thing here. The bottom value, or the minimum value, also decreases. The minimum for each one of these graphs decreases. And why is that so? Well, if we substitute minus b over 2a into y equals ax squared plus bx plus c, we replace the x with minus b over 2a, we get this, plus this, plus this. So all we're doing is replacing the x with minus b over 2a. Obviously, this is squared, and this is to the power 1. When we work this one out here together, we get b squared over 4a. This one becomes minus b squared over 2a. And of course, this doesn't change as c all the way down. So now we take a common denominator for a, and the first term becomes still b squared because this is the same as that. We're going to multiply this by 2 and get minus 2b squared. And we're going to multiply this by 4a, and we get 4ac. Let's put this term right over here because it's positive. B squared minus 2b squared is minus b squared 4a. So value, minimum value, will decrease as b increases because this term is negative. You're squaring it, and as b increases, it will be more and more negative, and will move the y value to the left. what about changing C? Again, here we're going to assume A is greater than 0 and B is greater than 0 here. You can see we put A equal to 1 for all of these, B equal to 1 here, and all we've done is change C. Now the y-intercept is the point where the graph crosses the y-axis and where x equals 0. So in order, if we look at this point right here, and it comes from this graph, this intercept right here is obtained where x is 0 along this line. So y is equal to c here. The other graph, you can see there's the y-intercept and there's the y-intercept. So here, the 0 is right here. It's the y value. It's y equals c. Here it's 1, okay, because we're 1 value here, and here is 3. So what happens is as y increases, okay, as C increases, so if we look at C, where C increases, the y-intercept increases. Now, we're going to set up a template for calculating and solving this graph here. We'll look at this, show the parabola and calculate the intercepts and vertex. Now, I'm going to pay particular attention to the intercepts and the vertex because, and the calculation of them rather than just showing the parabola. If I put this generic equation into ax squared plus bx plus c, I put a equal to 1 because the coefficient here is 1. I put b equal to 2 and c equal to minus 8. So here's b to c equal to minus 8. The combination of entries into box 3, 1, 2, 3, and 4 will give me this graph here. Will give me the parabola. Move it down a little bit here. Okay. So, but what I want to do is do the actual calculations and confirm what I see obtained from boxes 1, 2, 3, and 4. So to get the x-intercepts, I solve the quadratic equation, and we call x sub 1 one of the intercepts, where I have minus b plus square root of b squared minus 4ac over 2a, and x2, where we get minus b minus square root of b squared minus 4a over 2a. Here we see the calculated values of the two x-intercepts as 2 and minus 4. So here you see the 2 value, here you see the minus 4 value. So I've calculated the x-intercepts, and I've showed them that where they exist on the graph, which was obtained from the entries in box 1, 2, 3, and 4. Now, the next thing I do is calculate the axis of symmetry, which is minus b over 2a. So the axis of symmetry is right here, x equal to minus 1. Not be able to see that. Let me move it up a little bit here. There you see x equals minus 1, so it's the line that runs along here. And it's calculated. I calculated here. I'm not graphed it, I calculated it. These boxes here show calculated entries. If I see this here, this indicates that it's going to show me a graph. Okay, so now once I've got the axis of symmetry right here, I can plug that into the equation for the quadratic equation and get the corresponding minimum y value, which is minus 9. So there it is right here. So this point right here is minus 1, minus 9. Now what I've done is I want to show the points myself without clicking on the graph at all. So I've entered these 4 points. There's the first x-intercept. There's the second x-intercept. There is the vertex, and there is the y-intercept. Now I know what C is. C is minus 8. So the y-intercept right here is 0, comma, minus 8. And I get that. That point is because I put this in here. So these points together all lie on the graph and corroborate they're where they should be. If these points, if I had done these calculations incorrectly, these points would not lie on the graph. Okay, so now what I can do is, let's just go over there. Box 1 gives me the parabola based on the values of A, B, and C, and these are the sliders for A, B, and C. So you're not going to see these graphs until you put the sliders in the graph. You must, 1, 2, 3, and 4 go together. 5 and 6 are the calculation for the x-intercept. 7 is the calculation for the axis of symmetry. 8 is the, in this case, the minimum value. And 9 is the graph points. Now, there's a much simpler way of doing all this, in a sense. And I could just put into box 1 this, and then use projection mode, click on these points. Here you see the 2 x-intercepts. Here you can see very clearly the y-intercept. And here you can see the vertex. And you say, well, why didn't you just do that? Well, because really when you're doing that, you don't know where these points are coming from, how they were obtained. So that's why I do the calculations to show where these points were obtained. Now what I'm going to do is just change the parabola, the quadratic equation to y equals minus x squared minus x plus 6. And all I have to do is change the value of the sliders. A is minus 1, B is minus 1, C is 6. And automatically all the calculations will be made. I've used exactly the same template as before. So all I've done is put in the values of A minus 1, B minus 1, and C is plus 6. And of course the graph, because the coefficient of x squared is negative, the graph has to be shaped like a frown, and you can see where it is right here. And you can see here is the vertex, and the vertex is at minus 0.5, comma 6.25. Where do I get that from? Okay, minus 0.5 or minus a half. And when I plug that into that, I get the maximum value of 6.25. So you can see right about here, 6.25. This is 6. So this is minus a half. So if you go up from here, going up right here, minus a half, and the y value is 6.25. Okay, one of the x-intercepts is minus 3, agrees with that. One of the x-intercepts is 2, agrees with that. And of course, the y-intercept has to be at 6 right there. Now, here we have page 122, number 8. The height in feet of a ball x after being thrown is given by h equals minus 8.5x squared plus 25x plus 6.5. After how many seconds is the ball's height less than when it was released? When does the ball land? And when does the ball reach its maximum height? What is the maximum height? Well, this is where Desmos comes in really very useful. What I've done here is to enter the quadratic equation right here. I put in the coefficients given, minus 8.5, B is 25, and C is 6.5. So I immediately get this graph right here. Now, really, you don't need to worry about this part because here's the ground right here along here. This represents the ground. And here's when the ball is thrown, because the ball is thrown at time 0. So the time is along this axis and the x-axis, and the height is the y-axis. So we start here essentially is where the graph is drawn. So I start from 6.5. Okay, I start from 6.5 height, where it's thrown, and it's thrown upwards, and it reaches its maximum height, 1.471 seconds. And the height at this 1.471 seconds is 24 feet. Then it starts to come down, and it reaches our initial height of 6.5 feet in 2.941 seconds, and then starts to drop, and right here it hits the ground. So it hits the ground at 3.182 seconds. Remember, the x value here is the time, and the y value is the height. The x value is the time, and the y value is the height. Calculated the axis of symmetry, calculated the maximum height, and this corroborates what I see in the graph. This is calculated. Now I can just click on this point in the graph itself, and it'll give me this point if I click on it. So what I've done here is draw a line in for 6.5 feet. This is where the ball is initially thrown. Here's the person, and he's throwing the ball up at 6.5 feet, goes up, comes back down, and then after 2.941 seconds, after this, its height drops below what it was initially, which was 6.5, which is the reason I drew y equals 6.5 here. Then, after 3.182 seconds, it hits the ground. In other words, the height is 0. So, from the y-intercept, the ball is thrown initially from a height of 6.5 feet. The ball will have a height less than this after 2.941 seconds. That's right here. It drops below 6.5. The ball will hit the ground at 3.12 seconds. That's right here. The ball will reach its maximum height at 1.47 seconds. Let's show that right here. And y value at this time is calculated to be 24.88. The 0.147, 24.88. This is the x value, and the y value constitutes the vertex. Now, here in problem page 123, 14b, we're given that a parabola goes through 3 points, and we need the quadratic equation corresponding to this parabola. So we have 0, 5, 2, 13, and 3, 26. Now the key thing is to get right away on this point here. Since x is 0, this must be c, because y is always equal to c when x is 0. So we know c automatically. That's the most important thing. Then we're going to use these other 2 points to calculate the values of a and b. So we know c to start with is 5. We use these other 2 points to establish values a and b. So how do we do that? So y equals c when x is 0. So from the point 0, 5, you know that c is 5. From the point 2, 13, this is the x value and this is the y value. We plug this into y equals ax squared plus bx plus c. And y is 13. We're going to say x is 2, so 2 squared is 4. And x is 2 here, so we get 2b. And c, we know, is 5. So if we bring this 5 from the right to the left, we get 13 minus 5. We get 8 is equal to 4a plus 2b. And on this equation, x is 3, y is 26. We plug it in here, y is 26. A is 3, x is 3. 3 squared is 9, so we get 9a. And here x is 3, so we get 3b plus 5. We transpose this 5 over to the left, and we get 26 minus 5, which is 21, is equal to 9a plus 3b. So we now have two equations and two unknowns. So what we can do now here is that we can't, so this is in Desmos, we're going to replace the coefficient a with x and replace the coefficient b with y, because we'll only be able to get equations if these are in terms of x and y instead of a and b. So right over here, I'm going to say 4x plus 2y equals 8, and 21 equals x plus 3y. So we're just replacing a and b with x and y respectively, and that's what I did over here in these two boxes here. So I get each of them, and the intercept is b, because this is x and y, but I said that x equals a and y equals b, because that's the only way Desmos will solve this graphically. So, very simple. I automatically now know the values of a and b. So all this is extra down here. Now I'm going to explain what I did here. I took this equation and I'm going to calculate the values of x and y. So I've got 9x plus 3y equals 21. I put 9x plus 3. And instead of y, I'm going to solve this equation for y, which is 2y equals 8 minus 4x, because I'm going to transpose this. And so y becomes 8 minus 4x over 2. So instead of the y here, I'm going to replace it so that everything is in terms of x. See, everything is in terms of x, and it tells me that x equals 3, which is automatically the calculated way that I see it here graphically. This is the point of intersection, which I just click on, and I get that value. Okay, so now that I know that x is 3, I plug x equals 3 back into this equation. 4 times 3 plus 2y equals 8, and y equals minus 2. So I get the minus 2. So box 4 and 5 here are just the calculated values of what I obtained over here. You don't need to do that, but it just shows you a separate way. Now, what I did here in box 7 and 8 was first of all to put the equation in, because I know A is 3 right here. I know B is minus 2, and I know C is 5, and I get this graph right here. So there's the graph corresponding to that. Now what I do is I put the 3 points given in the problem, and lo and behold, they appear on the graph. If this equation was not right, these points would not fall on the graph. So A equals 3, B equals minus 2, and C equals 5. A equals 3, B equals minus 2, and C equals 5. Find the 2 points of intersection of the line and the parabola. Well, this is very, very easy here. I just put this equation in, and I put that equation in, the 2 equations, and I click on the points, and I look for the point of intersection right here. We got 1, 3, and 6, 8 are the points. Here's the straight line represented by this equation, and here is the parabola. And you see, just to check a few things, C is equal to 8, so that's right. And here, you could set x equal to 0. When x is 0, y is equal to 2. So, got that here. x is 0, y is equal to 2. And if you set y equal to 0, x is equal to minus 2. So that's right here. Just some additional things that you always like to do. Just check that you have everything right. Now, there's another way that we can do this. And what we can do is put in the points 1 and 6, the x values right here. The points, x values of intersection. Just to confirm it, put in the points 1 and 6. Then what we can do is a table of values, and you can see that you put in equation y equal x plus 2 here, and you put in this equation here, and it calculates the y values, and the y values must be the same here because they are the points of intersection. So 1, 3 lies on the straight line and lies on the parabola. 6, 8 lies on the straight line and also lies on the parabola. You can see that right here. 1, 3 lies on the straight line. It also lies on the parabola. 6, 8 also lies on the straight line and also lies on the parabola. So we just a little minor thing. You don't have to do this because it's already shown on the graph, but it's just an interesting thing. How to confirm using Desmos, how you can confirm answers and corroborate. So this is our